This video then, friction on an inclined plane, combines three of the previous videos. One is resolving forces, the other is equilibrium, and the other is friction. So there's nothing new in what you are going to see, it's just a combination of those things. So we have our object at rest on a rough inclined plane. What are the sources of forces? As ever, that's the first thing we should be thinking about. Well, the weight component, it's in contact with the surface, so there's a normal reaction. It's a rough plane. Now, this object ordinarily, without any push or pull forces, would want to slide down the plane, so friction would be acting in the opposite direction, because friction always opposes the direction that motion is trying to be made, so that would be up the incline. So we resolve the weight parallel and perpendicular to the plane, as we've done on previous videos. So that would be mg cos theta and mg sin theta, sine down the incline. It's in limiting equilibrium, so friction would be at its maximum, which would be mu r. And so those would be the forces acting on the object parallel and perpendicular to the incline. Parallel, we'd have mu r equals mg sine theta because we have equilibrium, and perpendicular r would equal mg cos theta. If you wanted to try this as an experiment, you can actually calculate the coefficient of friction between two surfaces. If you divide equation 1 by equation 2, you actually get mu equals tan theta. Therefore, if you have a table with, say, a book on it, and you tip the table upwards just to the point where the book starts moving, starts sliding, okay, then the coefficient of friction mu will equal tan theta, where theta is the angle of incline of the table. So here we have our object on our incline. Again, what are the sources of forces? Well, there's the weight. It's in contact with the surface, so there's a normal reaction. And the object would wish to slide down the incline. Therefore, friction opposes that motion, so friction will act up the incline. We resolve the weight component into the incline and parallel to it. So those are our two components of the weight. So now the forces on the object, well, in limiting equilibrium, so F equals mu r, it is at maximum, remember, so that's 0.2 times r. Into the plane, we've got 3g cos theta, and down the incline, 3g sin theta. Therefore, that gives us 0.2 r equals 3g sin theta. Perpendicular, we have r equals 3g cos theta. And if we divide equation 1 by equation 2, when we do the division, 3g and 3g will cancel out. We'll be left with sine over cos, which is tan. And on the left-hand side, we'll have 0.2r divided by r, and that will just give us 0.2. So there we have our result, that tan theta is 0.2, so theta will be 11.3 degrees. Here in this example, we've got a horizontal pull force or push force, it does not matter. We've got the weight of 1.5 g, we've got a normal reaction r, we've got a rough plane, so we've got friction. Now I'm just going to put friction up the incline in this diagram. We can carry out a quick calculation and work out in actual fact the direction that friction should be in. It would all be a matter of whether the component of the 20 newtons up the incline will be greater than the 1.5 g component down the incline. If you put friction up the incline and you end up with FB negative, it's just telling you that friction is acting down the incline. So let's resolve the weight into its two components. Let's do the same for the horizontal 20 Newton force. So that's theta, so up the incline will be 20 cos theta, and into the incline is 20 sine theta. So now those are the forces on the object. We've got 20 cos theta plus F upwards and 1.5 G sine theta downwards, and then perpendicular we've got R equaling 1.5 G cos theta plus 20 sine theta. And resolving that, we find that R is 22.7 to 3 significant figures. If we wish to find the magnitude and direction of the frictional force, then parallel to the incline, so that's a little notation there for parallel, we've got 1.5 G sine theta equals 20 cos theta plus F. And there we do indeed find that F is negative. So in actual fact, its magnitude is 9.97. The direction of it, because it's negative, and we had it acting up the incline, in actual fact, it's acting down the plane. For part C, to find the minimum value of the coefficient of friction, remember F is less than or equal to mu r. It only equals mu r when it's at its maximum. So mu r then is greater or equal to 9.9705. Therefore, dividing by 22.7305, which is the value of r, mu therefore is greater than or equal to 0.4386, which is 0.439 to 3 significant figures.